Oh, sorry. Okay, sorry guys, I didn't recognize. Let us start. I'm gonna review the what we talked. Okay, I at the first of the session I explained and like reviewed what we discussed in the previous sessions about the grid following inverters and what are the requirements of the grid following. We wanted to like follow whatever demand the grid has. And then we went to the part that, okay, if we want to like follow the grid, that means we have to measure what grid wants and then change our setting to mitigate the error between our setting and the measured or like demand of the grid. So that means we need a feedback controller. We talked about the PID controller in the previous session, and we uh, gone through the detail of how we could like have a PID controller as a second order controller or a PI as a first order controller. We already discussed the detail on that. One of the aspects that we said about the grid following is that our inverter should also follow the frequency of the grid, meaning they have to have same frequency. Therefore, we should synchronize our inverter to the grid all the time. Okay. For synchronization, I made these two examples, A1 sine omega 1 theta 1 and A2 sine those two sinusoidal voltage. And I said, when we want to say synchronization, that doesn't mean that we have to make these two parentheses equal to each other. It means that we have to make these omegas equal to each other, meaning they alternate in a synchrony. Okay, so the alternation are synchronized, not the exact values at each time. Okay, so this is one aspect. And then we gone through the PLL and said, okay, if we wanted to like synchronize our inverter with our PLL, with our grid, we use a technology or method named phase lock loop, which has tons of other application beside that. What we wanted to use that PLL for is to synchronize our inverter to the grid. And we said, okay, this PLL would have three main component in order to measure the frequency of the grid and try to eliminate the difference between the already existing settings in the control system and the measured frequency at each time. That means because it tries to mitigate again the error, that means the PLL has a kind of like aspect of PID control within it. Okay. The three main components of the PLL are the phase detection, which detect the frequency of the measured waveform at our point of connection to the grid. There is going to be a loop filter. We are going to see why we need loop filter. Okay. And the next component is the VCO or voltage control oscillator, which when you detect the frequency, you want to create a sinusoidal signal with that frequency so you could have your reference signal for your PWM. Okay, that is what we talked so far, and I'm sorry that I didn't realize that is mute my Zoom meeting. Is there any question so far about those concepts that we talked about, you guys in the Zoom meeting? Any question? No? Okay, let's move forward then. Now, we said we have three component, phase detector, loop filter, and the BCO. Phase detector job is to detect the frequency. Okay, there are several methods. We are gonna, if you wanted to like do the PLL in your simulation or you wanted to like apply in our course, we are gonna choose the simplest way. I'm gonna introduce three PLL methodology, phase detection methodology, okay, that is used in industry. We are gonna use the first one, okay, the simplest one. Okay. to detect the frequency, we are going to talk about that, how this methodology works. But why we need loop filter? We want to like create, we want to like detect the frequency of the waveform, okay? And create a signal with that frequency. What is the significance of loop filter? Anyone can tell me or kind of like guess why we need a loop filter or like simply filter in order to uh, in our PLL system.
To make sure it keeps going back through to keep it in phase.
The phase detector will always is continuous time, will always detect the phase or to be accurate frequency of the grid.
But you have to keep
And
making sure that the signal is correct.
this is our system, okay? This is our system. This is our measurement. This is our measurement. Okay, so grid is here. We calculate, we send the waveform here. We calculate the frequency of the grid, okay? And what we want is a reference frequency for our PWM, which is done by VCO. So we calculate the frequency, and this VCO would create a sinusoidal with that frequency. What is the significance of this one here? Reduce error is not a good terminology, but that's you're in the right track. We are talking about a real world application. The frequency, as we said, is not going to be 60 hertz all the time, first. Plus, is not going to be, our measurement is not going to be noise free. Okay. So if you do not filter out the noise from your measurement, you are going to have a slightly different, okay, frequency detected based on the real frequency that exists in the grid. So, yeah. So the filter actually what it works is to eliminate all those noises and unnecessary high frequency variation. Okay. So that way your detector signal is smooth, so you don't, those noises would not affect your oscillator when it wanted to like create a sinusoidal voltage based on that real-time detected frequency. Exactly. Like PLL has a lot of application and is very kind of like interesting. Search on that. It's a very interesting kind of like tool in different areas. What we are gonna use it is just a frequency detection and synchronization, but it has a lot of application. Now, when we detect the frequency and eliminate the noises, now we had a solid number, a solid value as our frequency to control, to like reset our PWM inverter setting. Okay. And the VCO comes in that point. We have our new frequency. The VCO would create a sinusoidal signal with the detected frequency and send it as a reference to our PWM. So so far, like in the task one, I believe you already implemented a PLL in your assignment because MATLAB has already a PLL. You don't need to like create a PLL. It has a PLL module. Okay, but if you want to like do that, you can like use this the video that I sent you in the announcement and the videos here and the concepts here to like create your own, you know, module of that PLL. But before you add the PLL, what you used for the sinusoidal PWM was to basically compare a sine voltage. You put a sine generator and a triangular generator, and based on the comparison of these two, you create your PWM. Now what's going to happen is that the VCO here is going to replace that sine generator. Are we good? So now what create that sinusoidal voltage is the VCO in the PLL. So this output is that reference voltage, the reference signal in your PWM. Is that clear? Any question about that?
Which one? The sign or the triangle is what goes to?
The sign, the reference one. This VCO creates a sinusoidal voltage, which you can use for your reference because it has the proper frequency.
But we need it.
Before implementing a PLL, you had a sinusoidal voltage source using in your PWM system. Now that you wanted to like apply PLL, PLL should define that sinusoidal voltage. It's not the same because your frequency of the grid is changing. If you have like a solid sinusoidal generator, your frequency is constant. It won't change. But you want it to be changed if the grid changes frequency. So you need to have a dynamic kind of like system when the VCO actually in real time changes the frequency of that sinusoidal based on the measurements.
If you're feeding it the sign, the point, are you saying change that sign that we're generating to a gigantic one?
Is not a constant. So that's what I'm saying. When you add PLL, this VCO, the frequency of the VCO is decided based on the real-time measurement.
Thinking it constant.
No, it's not. No. See, this was the PWM. MATLAB also, like this is the MATLAB, okay? You had a reference, you had a triangle, you compare these two with each other. Whenever it was greater, the reference was higher than the triangle, you would ignite the switch. Correct? Now, before you had a sine wave generator in your MATLAB system with a constant frequency. So the frequency was a certain constant. Now in this version, we are gonna have a PLL, okay? Based on the module that you use, either this PLL output is frequency, the detected frequency, or it has already a oscillator, a VCO in it, which actually outputs a sinusoidal with a frequency that is equal to the frequency of the grid in real time. Here. Oh, the grid voltage. Like you have inverter here connected to the grid. Yeah, okay. Yeah, sorry. I wasn't is that clear now? Yeah. As the grid.
Then probably what you because if we have a new reference, okay, reference signal now, because reference signal affects don't you need to have maybe two controls, maybe that nested things control the amplitude of the reference and then the previous.
Amplitude of the reference. What would be the amplitude of the reference change? We talked about that in previous session.
Yes, now why should the PLL? So inside the PLL, do you have that part?
Yeah, two different idea. Okay, PLL is not a control per se as like controlling the output. Okay, that PID controller controlled your active and reactive injection. Okay, now what happens in the system is that you have a sinusoid, a reference, and you have your triangle. Okay, now to create your PWM. Okay, we said based on the amplitude of our voltage, we could control the reactive power reactive power interaction. Okay, so who decide the amplitude? The amplitude of our reference, which is modulation index. You remember that? So by changing modulation index, we could change the level of voltage at the output of inverter, meaning we could either inject or consume reactive power. Again, we said if we wanted to like control active power, we had to control the theta, the phase angle of our waveform, of our output. What is going to be the phase angle of our output? The phase angle of our reference signal. Okay, so if you wanted to like inject more power, you have to have a little bit more delay, a lag or lead, based on whatever you want to do. Okay, for phase angle, initial phase angle, that constant number, not the omega, that theta. Okay, by changing the theta of the reference signal, you're changing the theta of output of the inverter, which means there is going to be a difference of the theta between inverter and grid, meaning we have a flow of active power in some direction. Okay, now for control of the dynamic or like a response to the grid, we control modulation index and the theta of that reference signal. Okay, so that's what we control for voltage and current control. Are we good so far? Now, this is a sinusoidal signal. Okay, the reference is amplitude, which amplitude is M, a sine, an omega reference, plus theta. This decides active power, this decides reactive power. Okay, what about this guy? That's where the PLL comes. Now, PLL tries to keep it synchronized, keep that omega synchronized with the grid. Why is it important? Because let's say we have a slightly less frequency in our reference signal than our grid. So we are out of synchronization. And the frequency of our inverter is a very tiny, less than the frequency of the grid. Okay, we are talking about a time variant waveform. Time variant waveform. So this is our grid. And a slightly less. This is our inverter. Correct? At each time, when the system wanted to decide how much active power it should drain from the system, it look at the theta that it sees from the inverter and the grid connection. The system doesn't know we have a slight frequency change. So it's assumed that our inverter works perfectly and synchronized with the system, but in reality it's not. Okay, so when it sees like in this time, when it tries to see what's going on in theta between the difference of theta between the inverter and grid, it translate that difference caused by omega t. This is, let's say, omega r is omega of the grid plus a delta. Okay, then the phase of the grid, the phase of the inverter is always going to be omega grid plus omega grid theta plus delta theta plus the inverter theta. Correct? System would assume this part as initial phase angle because it says it's kind of like the assumption is that the omega is synchronized for the system. So if you're out of synchronization, what systems would see that out of synchronization is the different phase angle. So you would lose the control of active power injection. It would be an error in your active power injection. Do you see what I'm saying? So any deviation from the frequency would be translated to the change from the system perspective to the change in a phase number, meaning it would change the active power injection, meaning you lost the control of your active power injection into the grid. Okay, and it's continue to vary because it's not like solid delta t. When t is changing, it's time. T is changing, it continuously varies. So basically, you don't have a solid injection of the power grid. You have something like haphazardly changing injection of the active power. Is that clear?
Yeah, yeah. So, so why do we need? Because from what you said, the PLL only controls the
Yeah.
of the frequency.
PLL would make this delta go to 0. Okay, so now you can there is no variation. You can trust your control system on active power injection. So we need to be synchronized because of that. Are we good? Did that answer your question? So PLL make sure that this reference signal has the omega that it need to have in order to avoid that variation and that problem in the control system.
So how do this control?
It is a single kind of like system. What PLL do is only tries to control, okay, the frequency of a reference signal. So what's happening is that you have a PLL. A PLL would create for you a raw sine voltage. Then this raw sine voltage goes to your PID controller, which set the MA and the theta applies to that raw sinusoidal and give you your reference voltage for PWM. You see what I'm saying? So this is kind of like the situation that's going on in the control system. Are we good? Any question? Which one?
Bottom drawing. One of them saying Clark and one.
Oh, different transformation. Different, they are a mathematical transformation. You can search on that. They are too advanced for this code. I don't want to like you to implement that in your system or like you, but if you learn that is quite good. Okay, I am gonna talk about it a little bit later on in a system analysis after the midterm. Okay, but it's kind of like a more advanced. There are two mathematical transformation. Yeah. This is the zero detection. This is the SRF PLL. This is the SRRF PLL. Yeah. Now we said that the first component in our PLL is the phase detector. We have several technology or methodology to detect the phase of our inverter. The simplest one that you need to like implement if you want, if you don't want to like use already existing PLL in MATLAB, is the zero crossing detector. Very simple, very simple. What it does is to just like a clock count how many times the signal crosses the value 0. Okay, so if you have a sinusoidal, it would count the zeros, the crossing of the zeros, and based on that, it counts how many alternation you have, ergo the frequency. Very simple. Okay, but it comes with a cost What is the cost? If you have a noise or variation or harmonic. This is a pure sine. In reality, life is not that pure. So what's going to happen is that you have like a very kind of like, I wrote it very badly. No, 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 no. That is, how can I, okay. Let's say we have a harmonic in our sine. Okay. Now you can see that our distorted voltage would not simply cross the zero line on the like 180 degree and 360 degree. Because of the harmonics, there are some variation. It makes it cross the zero line more than it should be. So the zero crossing is very sensitive to the harmonics and noise because it just simply count how many times you cross the zero. If you have a noise, that means you count the noise too. Are we good? So very simple. Now, to answer that problem, we introduce another method named stationary reference frame PLL. Okay, what stationary reference PLL does is that it tries to observe the waveform, okay, multiply it to a sine once, and then to a cosine in another way, and then compare and then use the sine version and cosine version in order to detect the omega at each time. You don't need to like worry about the mathematics. I think I already put that in a reference book. There is the description about the SRR. Okay, but what it does is that it has a stationary frame, a triangular mode that's sine cosine. Okay, which here you could see it as DQ mode. DQ mode. Okay, DQ mode is a two-dimensional signal. Okay, so same goes with the imaginary real Cartesian, sine, cosine.
Can you change
Yeah, so
rectangular?
exactly. So you have a sine, cosine version of your signal, and based on that stationary frame, you can analyze what is the difference of the frequency. If there is a difference of frequency, your vector is going to be rotating. If your vector is solid in your system, that means you have zero frequency. If your vector is changing, that means between the sine version and cosine version, there's a difference of frequency. A stationary frame system. What happens in the more advanced one that we don't have a stationary frame? We let the frame place too. So this is more advanced. Why is more advanced? Because if the grid is unstable or unbalanced, then a stationary frame would not work. Why is that? A stationary frame works with a transformation of three-phase to DQ system. Inherently, by that transformation, within that transformation, this SRF, okay, inherently assumes that all the three phases are balanced with each other. Okay, what we assumed in power system, like if you had like a energy conversion, we always assumed in the energy conversion example and question that we have a balanced system. But we know that in reality, that's not going to happen. Okay, so when you have an unbalanced system, there is going to be an error in that transformation, meaning your frame, your stationary frame for each is not real, is under an assumption. So there's not accurate kind of like transformation. How we could deal with that? By using quark transform and Park transform in a series of each other. You don't need to like worry about that. I'm not gonna ask you to implement that, but I just want to like get to know these ideas. Search on that is a kind of like interesting idea. I'm gonna talk about the Clark and Park and DQ later on, introduce them, but you don't need to worry about them. Now, by using these two transformation, they create a dynamic frame. So now our frame is not solid, is not uh, constant, stationary. It's actually rotating reference frame. Meaning if you have an unbalanced, it would show itself in the frame and you adjust the frame based on your already like real condition in the grid. And after you adjust the frame, now you try to like calculate the difference of the frequency if there is. This is the intuition wise. Mathematical wise, I'm gonna give you some aspect, and you can search that. It's not honestly, is mathematical wise is not that hard to understand. Okay, it's simple transformation, so it's just like a matrix that you multiply with your input and gives you the new values. Okay, but you don't need to implement that in your project. Any question? Yeah. How expensive filter you can choose, you know? Still, even if you choose filter, you still will have variation. Is not perfect. So if you have a lot of harmonics or noise, that's gonna be problematic, especially high frequencies. Because even if you have a low frequency, low pass filter, in an ultra high frequency, low pass filter would not work. I think I mentioned that in a high frequency, there is going to be a parasitic capacitance in a low pass filter that actually let go of the ultra high frequency. So low pass filter is not like it let go of the low frequency and then cut the high frequency. After a certain amount, because of the radiation, parasitic capacitance, it goes up again. So ultra high frequency would pass through a low pass filter. Are we good? Any question? No? Okay. Now, we already said that, okay, we have several like problems that could be faced in our system, in our PLL system. One is the harmonic. We said about that. We talked about that. If there is a harmonic distortion, what's gonna be what we have to do? And the solution that we had is to move on from zero crossing to a more kind of like sophisticated, more advanced techniques in order to like eliminate the harmonic. Why we eliminate the harmonic using SRF? We said SRF is multiplying the output to a sine and a cosine. Okay? Fourier series. If you multiply to one sine with a specific frequency and one cosine with a specific frequency, basically you could eliminate all the other. Okay? Read about the Fourier series characteristics. Okay, and how different frequencies of sinusoidal, if you multiply them with each other, what's going to happen? How they would react. Then you would find out that it's actually the only way that you can turn a sinusoidal to a constant value, to a DC value, which was the purpose of the SRF, is to multiply it by the sinusoidal with the same frequency. Then you have a constant value. Is that clear? Are we good on that? Any question about that? Is a trigonometric relation. Google that, like what is the omega, like what is the sine multiplied by sine? It would give you the formula, and you would see if the omegas are equal to each other, you would have a DC component in your result. Now, if you have an instability or like imbalance in your system, we said that's going to be a problem. Again, we could have like a more advanced technique like a FFT PLL that deal with the instability by going toward the frequency domain, or like LN, LPN. These are, I'm gonna just name them in order to like you be introduced to them. You could search on that. These are the advanced PLL techniques to deal with that instability and unbalancing. And if you have a nonlinear system, which means your system, you can't count on an FFT because Fourier series is within a linear system, works within a linear system. If you have a nonlinear system, then there is going to be another uncertainty introduced to your measurement, okay, which you have to deal with that. And the methods like this DSRF PLL and DDSRF PLL are the ways to go. Now, any questions so far? These are just mentioning the problem and possible solutions.
By the way.
I don't know. Whenever I edit
Facebook
them,
loops
that
or
repetition
PLLs
is
for analog
done.
signals are ubiquitous.
But immediately after I edit that, it comes back. I don't know what's going on. Okay, let's go through this video. This is explain the PLL from different perspectives.
Applications. Frequency tracking, resonance driving, and oscillator control are some examples. Are you curious to know how PLL for analog signal work? Hi, I'm Anna, and in this video we talk about PLL working principles, how to set PLL up, and what different application use cases they are. Let's start. A PLL keeps the phase difference between a reference signal and follower oscillator at a fixed set point by adjusting the frequency of the oscillator based on the phase difference between two signals. It consists of three main components. The first element is a phase detector to measure the phase difference between two periodic signals. The second one is a PID controller or a loop filter, and this translates the phase difference into a feedback signal. And finally, the third component is a controlled oscillator whose frequency can be modified by feedback signal. To lock the phase between input and output signal, we need to close the feedback loop by applying the output signal to one of the inputs of phase detector. If properly adjusted, the phase difference between the input and output signals remain constant in time, and therefore they run with the same frequency. Now let's focus on these components one by one. Depending on the signals and use cases, different approaches can be used to measure the phase difference between two periodic signals. When using analog signals, a dual phase demodulator, which is the core of the lock-in amplifier, can take a reference signal and an input signal and derive the two quadrature components X and Y. From those, the amplitude and the relative phase can be obtained. The measured phase covers all four quadrants of the whole circle from -180 to +180 degrees. The next step after measuring the signal phase is to transform it to a feedback signal. First, the phase is subtracted from the target set point to generate an error signal. Then the error signal is passed through proportional, integral, and derivative operation to adjust the feedback dynamic according to the application requirements. After adding an offset and limiting the signal range, the final feedback signal is ready for the third component, that is the controlled oscillator. In order for PLL to work properly and efficiently, it is crucial to use the right P, I, and D parameters. Finding the optimal parameters is complex, but no worries. We will introduce you later to our PID advisor, which helps you design an effective PLL. The last building block of a PLL system is an oscillator with the capability to control its frequency either numerically, NCO, or by analog voltage, VCO. This is the basic PLL functionality scheme. In addition to the three main essential blocks, a PLL can include extra functionalities to address some specific requirements. For instance, if you need to stabilize an optical interferometer over multiple wavelengths, a digitally implemented PLL can easily unwrap the measured phase so that it can build up beyond.
This is the other application of PLL that I told you. Like, this is a very good video. I posted already my PowerPoint in the Canvas, so you could like go through that video and read the other application. But let's move forward for our own application. Any questions so far? Is that clear how PLL works? Are we good? Okay. Now, let's try to talk about the actual like implementation of those concept. Like, if you wanted to like implement a phase detector, okay, the simplest way to implement a phase detector is in analog system is D flip-flop, okay? What's happened is you can use two D flip-flop in mirror with each other, okay? That these two would control the input signal and reference signal, and if the frequency of the reference signal is higher than the frequency of the measured signal, then the up switch, the up gate is going to be on, and if there is a reverse relation, the down switch is going to be on, okay? Meaning it would increase the order to increase the frequency or decrease the frequency. And this is kind of like the analog circuit of a D flip-flop. I have to like practice that. Using the MOSFETs or like IGBT, or like even you could use BJT, it doesn't matter. If you wanted to like implement that D flip-flop circuit, this is the analog circuit for that. Okay. Since we already kind of like decided to like waive the hardware tasks because of the problem that we had for the delivery of the components, so you are not required to do these, just for your own kind of like information. Okay. Now, one thing that in reality works, okay, but in theory they don't mention it, is the charge pump component within the PLL. What the charge pump do is to sense that up-down signal from that D flip-flop, okay, and change them, translate them into a current signal. So basically, it's like a voltage source or a current source, to be precise. A current source that you get the signal up and down, and it will translate it to a certain amount of current going through the output of the charge point. Why we need that? Because for our oscillator, we need an analog signal rather than a digital up-down signal. This is kind of like a practical kind of like point. Okay. I also put the schematic of the charge pump used in like a very basic PLL that translates these up and down system into the output, into current for the output, and feed it to our filter, to our loop filter, to decrease the noise and variation, stabilize the values that we have to inject into our voltage controlled oscillator. The filter is pretty much simple. We already talked about the low pass filter. Like, for example, here you can see the RC filter, an example of RC filter that works with a PLL for a PLL. And it's actually the values are perfectly designed for a 60 hertz a kind of system. So by these values, you could filter out all the other like unwanted noises, and you have a stable, pure system at your voltage controlled oscillator. Very good. Now, the oscillator, normally they use a ring oscillator, okay, which it doesn't matter even if you don't want to like use the ring oscillator or like the schematic that I put here, okay, there's tons of other kind of like techniques to create a sinusoidal oscillator out of a signal, okay, but what it does is this ring oscillator actually get the uh, value of that current, that is current starving NMOS, the current that you get out of your charge pump, and then filter it with your filter, would get into your current starving NMOS transistor, okay? And using the schematic, it would create an oscillation in the output, creating a sinusoidal voltage with the same frequency that your PLL detect at your output. Again, this is for your own kind of like interest. We don't have a hardware assignment, so I don't want to go into that how this is working. But this is actually the exact design that like for a VCO that you need to put for a 60 hertz kind of like system. So your VCO would work. Like all the numbers are already designed for that purpose. Okay. So this is it. Is there any question regarding the PLL? No? For your task, as I said, you can use the PLL module in the Simulink, or you can create your own based on what we talked about today. Okay? You already know phase detection, how it works. You already know you need to have like a filter in it. You already know you have to have an oscillator in your PLL. You can create it your own, and it's not too hard. And I think I already put a video for that on the announcement. So let me know if you have any question about that. Any comment or question or concern? Are we good? Okay. Thank you very much. This is for today, and have a great rest of the day.